Just to give you an idea of what the induction factors are, you can see on the right hand side or left hand side for you guys that we have changed the definition of the velocity triangle. So if you look at the blade in turbine, it has a component in a peripheral or vertical direction, if you like, which is the peripheral velocity, which is the angular velocity multiplied by the radius. It has the wind velocity coming in this direction, and it has the relative velocity. This is simply called the velocity triangle. So U relative, and then omega times R. And we will use that expression many times because it's a triangle which we look at all times. And when we introduce the induction factors, we are changing that one to be we multiply by that one with 1 minus A, which is the actual induction factor. And this one we multiply by 1 plus A node. That means we are reducing this velocity, but we are increasing that velocity. So today we are going to introduce a way of designing the turbine without the induction factors, so that you understand the way of doing it. But the design you're doing now will be quite poor when it comes to actual wind turbine. So you need to optimize it on the way. So this is why we are doing the next steps. But first, I would like to go through a few things just to make you realize what is actually happening during operation of a wind turbine. Right, we have defined now that the relative velocity, the angle of attack. We have defined lift and drag, which again gives us torque and thrust. And now let's have a look at what will actually happen with a turbine during a wind gust. You're in this, the wind velocity is coming and increasing. That's quite normal in operation of a wind turbine. And the wind gusts, they can be quite tough or high. So for example, going from 10 to 15 meters per second in a wind gust, that's quite possible. For the components of lift and drag and all the things for a wind turbine, it changes the operation quite a lot. So let's have a look. All right, we are introducing a gust, meaning the wind velocity will change. So U here is increasing. Okay, what happens if U are increasing? The relative velocity is changing direction and magnitude. So the relative velocity will be higher, and on top of that you will have a higher angle of attack, meaning lift force will be higher and also the drag force. So this is happening to the lift and drag, and this is happening to the torque force, or the force in the torque direction and the force in the thrust direction. So you will have a higher force trying to push it backwards, and we will have a higher force trying to rotate it. The force is higher, the torque is higher, and therefore the the power output will be higher. Okay, let's assume now that we are operating on maximum power output. Let's say your turbine is going to operate at 1 megawatt, and the wind is actually blowing, for example, at 12 meters per second. Generator is working at its maximum. We can't go higher, and the gust is coming. 15 meters per second. Thrust force is going up, and that means the power from the wind is going up dramatically. The generator can't handle it because it's already at its maximum point. So what do you do? What can you do?
Some brakes.
You can break it.
Change the pitch.
Change the pitch. You change the pitch and you change the angle of attack. You lower the lift force and drag force. It's that simple. So that's why one of the reasons they have pitch on the wind turbines. All right, let's take another situation. We have a failure in the grid and it cuts. That means the generator is not handling, it's zero power on the generator. Generator cannot take anything. So that means that we are sitting with the wind from the power that is transferred to the shaft, but there's nothing handling the power output. Where is the power going now? What is happening now? Does it stop? No. The wind is there, it's still working. What can you use the power for? What is it? It's there, but you have to utilize it somehow. What can it be utilized for on this turbine?
Turbines have some resistors, some load bank.
That's
When the grid failure, the power will go to that load bank, and we will change the pitch of blades and turbine will stop.
That's possible, and some have. But let's assume you don't have resistors, you don't have pitch. This is your turbine, it's not going to have any pitch and no resistors. What happens if you lose the grid?
Keeps accelerating.
Excuse me?
It keeps accelerating. So
I didn't.
faster.
What happens to the velocity? Does anything happen? This is happening all the time for all turbines in the world. Yes, we have resistors and we can pitch it off, but if you can't do that, then what can you do? What happens? You have a mass there. There is a rotating mass. The generator and the turbine and the blades is actually just a rotating mass. It's a kind of a flywheel. And if you have excess power, then you can actually accelerate the flywheel. And that's what's going on. That's what happens. So the R times omega is going up. That's exactly what happens. So R times omega is going up. And now the relative velocity is going up, but the angle of attack is going down. And remember, the lift coefficient of the airfoils I showed you was if you had 0 degrees angle of attack, you have 0 lift. So it actually, what happens is that it will accelerate until you have zero power extra, or zero lift. So it's a kind of fail-safe situation. But this is what's going to happen. Most turbine manufacturers, they want to avoid this because centrifugal force can be too high when you accelerate this much. So they pitch it off, or they have a brake, or they have resistors to stop it. But this is an actual situation for wind turbine. So those two things, this is the way to think on the way when you design a turbine. You need to take these things into consideration. And later on I will introduce a few more things that is actually happening during this state of operation. Okay, now we'll start to design a wind turbine, and I will end the lecture with the exercise. And you're going to give the exercise as a table on Blackboard, so that you'll just turn it in that way. I will end up with that when I finish here. First of all, now we are dealing with your turbine. We have 0.9 meter in diameter, so that's the length of the diameter of the blade. We are going to utilize a wind speed of 12 meters per second and a tip speed ratio of 5. Let's define the tip speed ratio so that you understand what we are talking about, because it's a kind of an important factor. It is simply the velocity, the peripheral velocity at the tip of the blade, also the outer tip, divided by the wind velocity. So it tells you how fast the tip is moving relative to the wind. In this case, you are designing a turbine which has a tip velocity or peripheral velocity 5 times higher than the wind itself. We are going to assume that we can design a turbine which is 50% efficient. So the CP value is the efficiency, and we are aiming for 50%. This is an assumption and a simplification which we have to change later on. I don't think you're able to do it for 50%, but at least the first design you're going to make is based on these numbers. The wing profile is a NACA 23015. You don't have to bother about this time in this setting, because we have given you a constant angle of attack for all blade elements, and we are giving you a lift coefficient and drag coefficient which is the same for all elements. These are the things later on, these are things that you're going to iterate on, which is changing when you're changing the design. But in this case, in order to simplify a way of thinking, in order to learn and understand the procedure on how to design a turbine, we have given you this data. First of all, we need to define the power output from the wind. How much power can we extract from the wind itself? So let's define that equation and put it on the board here so we have it in our mind all the time. So power output will be density half multiplied by the wind velocity in the power of 3 multiplied by the area of the turbine, we call it area turbine, and then multiply by the power factor or efficiency, if you like. In our case, we have been given all these data. We know the density of the air, it's 1.2, that's what we're going to use. We know the wind velocity, which is given to 12 meters per second. We know the area of the turbine because we know the diameter is 0.9 meter. And we have been given 0.5 or 50% efficiency. So this we know. So that means we can actually extract 330 watts from this turbine if we succeed to have 50% efficiency. The speed of the turbine can be defined in two ways. One with the RPM, rotations per minute, or radians per second. In the equations we are going to use the angular velocity, which is radians per second. And we can extract that number from the TSR, the definition of TSR. We have, remember, TSR equals omega times R over U. That means omega is U times TSR divided by R. And of course the angular velocity is the same for all radiuses, but since TSR is defined as the tip speed, we are using the radius at the tip. So we are given those numbers. TSR is 5, velocity of the wind is 12, and the radius of the turbine is 0.45. So we can calculate the angular velocity based on that. And you can take the speed afterward if you like, but it's the rotation is you have 2 pi radians per revolution. So this is so that's the speed. The power output can be seen as something you extract from the wind, but you also have to look at what you can extract from the blades itself. So the total power is, and this is the key to the understanding of what's going on, because now we are moving to this is omega multiplied by torque in this case. And what is torque? Torque is the force in the torque direction multiplied by the radius. So this equation can be seen as the part which is coming from the wind itself, and this is what you actually are having on the blades, each blade. And since we have all of these numbers, we have that one. The unknown for us now is the torque. And the torque we will find from the forces on the wing profiles at each element. Now, I'm going to make you to think, we assume that the turbine is made out of several elements, and each element is simply a blade like this with constant chord length and constant depth, if you like. So when you design a turbine first time, the elements will look like this. It's like a stepwise distribution of the elements. If you use a good computer and you use 1,000 steps or 1,000 elements, you can make it look like this. But for the first case we are working with now, we are going to divided in 10 different elements. And we are going to do the calculations for those 10 elements. That's what I'm asking you to do, based on the equations that is coming now. So, first of all, I need to find out what is the torque on the shaft. And I can take that out from that equation. Since torque is the only unknown here, I'm able to extract that one, and I can calculate that. And in this case, it's going to be 2.5 Newton meter. And that's the torque on the shaft, and that's the torque from both blades. All right, now I'm introducing the fact that one blade is taking only half of the power and half of the torque, since we have a two-bladed turbine. So we are going to utilize the same equations, but we are going to extract the power from just a half a circle for the whole blade, and each element is going to extract its power from that donut like we are seeing there. So if this dr is a blade element length, and each element is taking the power from that area. So the power for one element is defined from the area which is extracting its power from. Apart from that, it will be the same way of thinking. So this area is simply if this is the element I'm talking about, then it's the circle of this circle minus this circle divided by 2. That's the area we are talking about. So that is included into the equation. So R in this case is the inner radius of the circle, and dr is the length of the element, and the outer radius is r plus dr. Okay. Now we are on the other equation. So now we know what each element can extract from the wind. So now we have to apply that power. Now we know that part, and now we have to look to this equation. Still, that one is constant, while this one is unknown. And that factor is simply the Ft, which is the force in the torque direction, multiplied by an arm, or a radius if you like. And now the point, that force is not acting from, if you have a blade element which has a difference of radius, the force acting from each element is acting from the middle of the element. Not at the outer rate, not at the inner, but at the middle of that area. Right. That's why we have R plus dr is half of the dr. You see? So that's the arm. So force multiplied by an arm multiplied by angular velocity is the power. And what is the unknown here? It's the force. So now I can calculate the force acting in, and now I have to calculate the force acting from each element in the torque direction. All right, so that means we're going to look at the blade. We have the blade. We have the lift and drag coefficients. We have the angle of attack. So actually the only unknown that we are looking for now is the chord length. That's where we are aiming. We're going to look at the chord length, and we also have to find out how much the blade are twisted on the way. So, you know these equations for lift and drag. They are the same as I told you earlier. And you know the definition of the velocity triangle. And we put this into the blade, which is rotating. And we are introducing some angles, which are the twist angles. And the theta value here is a twist angle. So that means how much is the chord line twisted relative to the vertical axis in this case? What does it mean on the wind turbine? If the wind turbine is, if I'm the wind turbine, it should be like this. Wind is, and it's moving up there. It's all about how much have I twisted this one relative to the vertical axis. It's all all comes down to geometry when we start to look at the velocity triangle. Because if we define theta plus alpha, or the angle of attack, we can define that as phi. And phi we can find in the velocity triangle. So the angle between the relative velocity and the peripheral velocity is phi. And if you know the angle of attack, you know the twist angle. That's the definitions. But for each and one of the blade element, you need to calculate the triangle and its geometry. And when you have done that, you are able to find the lift force in the torque direction, and you can find the drag force in the torque direction. And the summation of those will give you the force in the torque direction. So this is the equation you can use in order to find the force, which will be used to find the torque. I know I'm going fast now. I'm fully aware of it. So you need to repeat it yourself later on to find the total thing of it. But try to grab the physics of it and then later go into the details. So I can calculate the force from this equation. And the only unknown here is the chord length. Since you have the triangles, so you need to find the chord length of the blade. So we can extract that from that equation, and you can start to calculate your blade. That's all, guys. That's all. This is the way to design a turbine. And you can do that for all the blade elements of your turbine. So, I'm giving you, in this lecture note, I have given a table, and I want you to fill that table for me, each and one of you, and then that will be the answer to the exercise 1. All the equations you need is there. I only ask you to understand what you're doing, and then fill the numbers. So the exercise is then given here. So that's what I want you to do till next Friday. And when you go on the Blackboard, you'll find a possibility to hand in the exercise there. Just as a PDF for, I think Blackboard can handle almost anything. Questions?
We need to just give the table, or do we need to give in all the calculations?
You just give us just the table. That's all we ask. That's what we're asking for. All right then. Have a nice weekend.
The book, Wind Energy Explained,